second. I believe you can see my screen. And this is a presentation regarding the from CPU to GPU enhancing algorithm efficiency topic. And today, as the developers, we are always looking for ways to make code faster and more efficient, especially as our workloads grow more complex, data heavy. While CPUs have been our go-to most computations, they aren't always the best tool for the job. That's where GPUs come in. With their ability to handle thousands of operations in parallel, GPUs can dramatically accelerate many types of algorithms that struggle on traditional CPU architectures. Today we will explore the key differences between CPU and GPU computing, see where GPUs truly shine, and discuss how offloading and the right tasks can lead to significant performance improvements in real-world applications. So starting from the architecture differences. As you can see, I prepared the comparison table and for CPU general differences between the CPU and GPU architecture, and let's go deeper. CPU is just a central processing unit and GPU is the graphics processing unit. Previously, we used GPUs for rendering, for all stuff related to the rendering images and displaying the images on the screen on the monitors. But nowadays, we can use it for some other useful purposes. CPU have usually several cores nowadays. GPU a lot more, many cores, physical cores. CPU is low latency. It means that we can access the data from the memory really fast, but using the GPU, it's really like a bottleneck, a high throughput. Good CPU is good for serial processing, like one by one, and the GPU is definitely for parallel processing. Okay, for CPU can do a handful of operations at once, and for GPU can thousands of operations at once. Let's go next. What's the problems GPU solve better than the CPU? And I collected such like fields and areas where GPUs much better. And for example, for graphics rendering, as you know, you can also render images by CPU, but it's not really efficient. Graphics rendering is much better for GPU. Parallel processing, which I will describe today deeper. Matrix and vector operations. Initially, for rendering purposes, we operate with matrices and vectors because it's a lot of operations in this workflow, in a rendering pipeline and so on. And GPUs are great in this area. Also, scientific simulations. In these simulations, we can also use this parallelism that GPU provides us, and that's why we can use it in this area. Cryptography, we can also use this efficiently in this area. Signal processing, it is when we operate also with the images. Today I prepared the algorithm with the manipulations with the 2D images, and today we will look into this. and big data analytics. Sorry. Probably it's related to some AI and machine learning when a lot of data should be processed, and in this area we can use GPU efficiently. And what available APIs do we have to use this hardware, to use the GPU? The most famous, probably you already know about this, it is CUDA, Compute Unified Device Architecture. It is API from NVIDIA, developed by NVIDIA. And it's one of the most famous APIs for working with the GPU, but we have limitations using this API. We cannot, we stick to the NVIDIA graphic cards. Only these cards can be handled by the CUDA. If you use some like Radeon and so on, we should decide another API. For example, we have this OpenCL, Open Computing Language from open source, and we can use different vendors of the hardware. Also we have a direct compute from the Microsoft as part of a DirectX API. I actually didn't use it previously, but probably if we stick to the only Windows platform, we can try to use it and also compare the performance between, I don't know, CUDA, for example, and direct compute, but the operating system should be definitely Windows because it works only on Windows. Vulkan, it is really great, low level, lower overhead, cross-platform. I used it for rendering purposes, but I also know that we can use it for some of the computations. And OpenACC accelerator, it is another one, directive-based programming standard design. It is like an option also, we can use, try to use it. So we have some list to operate with the computations on the GPU, but for different hardware, for different operating systems. It is, the next slide is like a helicopter view of the architecture, how the data flows when we use the GPU in our system for computations. And for example, the data goes from some external source like hardware drive, sensors, other devices, and it goes to the RAM. It loads to the RAM. Then from RAM it goes to the, partially goes to the CPU, what needed for this, and also partially it goes to the RAM of the GPU. We cannot avoid using the CPU when we use GPU because we still need to go through to process the data from the CPU, and that's why it is present here. And here you can see it is a lot of blocks, and multi-streaming, multiprocessors. I will show you. On this slide, I would like to focus on the most famous API from NVIDIA CUDA, and what's the basic functions, workflow should be used to achieve like a hello world application for CUDA. The first, we should allocate the memory on GPU using the CUDA malloc, and we need to decide how many bytes we should allocate. Then we need to copy the data from the CPU to GPU using this function. The next, we should define the blocks and threads per blocks. To do this, it would be the efficient way would be to know what exact hardware do you use and what the efficient way, what the most the better numbers would be for this blocks amount and threads amount, because if use the default values, the performance could be not so great as we expected. So analyzing the particular hardware, we need to set these numbers for particular GPU. Also, we can try some different numbers and just to decide what would be more efficient. Then define and call the GPU function. So all we prepare it, then we need to define the function that will be executed particularly on the GPU, on the device. So we have like a host and device. Device is a GPU, host is like a CPU. And then when this function finished the execution, it means that all the data was processed on the GPU, and then all this processed data we should copy back to the CPU side, to the host, and then just free the memory that we previously allocated on the GPU. It is like a code workflow when we use the NVIDIA CUDA. It is like a basic approach. Nowadays it has like a managed functions, versions for these functions, but it is the basic one. And here we can see the again on the hardware. For example, we have in our CUDA program we defined 8 blocks. And for example, if we use GPU with only with 4 streaming multiprocessors, it goes to the first 4 and the second 4. But if our hardware can operate simultaneously on the 8 streaming multiprocessors, it could be just one on one hop. The data will be processed. It would be much faster and efficient. Okay, now I'm going to show a live demo. I prepared algorithm. It is Gaussian, so-called Gaussian blur. When we have an image, I prepared a really big image, like 5 megabytes HBAC, and I would like to apply the Gaussian blur filter algorithm to this image, and then compare the performance of the applications. So if we go to the main, probably should I increase the size of the text, or is it okay? Probably is it okay? Yeah. And so I have some preparations. I need to read image. For reading image, I used OpenCV library. When I read image to the data buffer, I needed to generate the Gaussian kernel, and then I'm going to to memorize the clock before the computations, not only before the but also before the memory allocation and so on. So it is really, I believe it is good for comparing the performance of these two types of applications, CPU versus GPU. So currently it is GPU. So then I allocated the memory for images input, temporary, and output. Temporary is needed to keep in the intermediate step, intermediate version of the image, and then just copy it to the output. And yeah, here I copied the data from the CPU to the GPU memory. And then you can see these two functions with really special syntax. It is with these triangular braces. when I set the number of blocks and threads. Yes, so I calculated it, as you can see, for particular my GPU. It is NVIDIA RTX 3070 Ti. And so I process image horizontally and then vertically. That's why you see these two functions. And after the processing it, I just compare the elapsed time, calculate the elapsed time, and print it to the output. And then after that, I just copy memory to the output, just to save it to the HDD to show you, and then just free the memory previously allocated on the device, on the GPU. Yeah, and it is implementations of this function, horizontal blur and vertical blur. It's really simple, but it is parallelized. And the second implementation alternative for GPU, I used multi-threading that we have in C++. I also used my Intel processor, which has 28 cores, and it's also pretty powerful hardware. And yeah, as you can see, I also created Gaussian blur, multi-threaded, vertical and horizontal, and join the threads. And when it's completed, I just clear, and again, then I compare some in my CPP. I just calculate elapsed time, and that's it. Okay, so I can show you. I'm going to show you these two versions. So on the left side, it is a CPU version of the application. And now I'm going to execute this and see the. Yeah, you see that it is 28 cores, and the execution processing time was approximately 3000 microseconds. I would like to execute it several times. I did it in advance, so it's approximately 300 microseconds approximately. And here on it is GPU version. GPU version. Let's execute it. The same input images is provided. So you can see that I calculate the whole time and just processing. What means processing time? It's the time of execution of this function that it executes on the GPU, not excluding the memory stuff like allocation, deallocation, copying, and so on. But if we also count all this memory management, it's still 140,000 microseconds. I'm going to execute it several times just to see the difference. The thread, because we need to, in the real applications, we need to warm up the GPU, because on the first steps it works really slow, but when it's warm up, the performance is much better. Yeah, you see that, for example, here there's 3000 microseconds, here is 117,000 microseconds, and I prepared the graphics, the trends. It is for CPU execution time, it is GPU, and you can see that it's approximately 3 times faster, but it's faster, but the cost of this hardware I mean, like this CPU and GPU approximately the same, but performance is much better. But it is what I'm going to highlight here, that the performance is great only for such kind of the tasks where we can use this parallelism. The bottleneck of using the GPU is the copying memory from the GPU to CPU and vice versa. It is really slow operation. So we need to create our applications in a way to reduce amount of these copying operations between the CPU and GPU. Yeah, and today I prepared a bonus for you. It is maybe you saw previously when Mythbusters created a demo when compared these two types of CPU versus GPU. Please let's see. It's maybe 1 minute of a video.
In the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3.
The first would be CPU.
1.
How CPU works. One core physical, yeah.
Ladies and gentlemen.
And this is the
Leonardo
GPU version.
2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet.
It is like a physical course, like a streaming multiprocessor, all these tubes.
When it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration. 2, 1.
That's it. Yeah. Yeah, Q&A session. Yeah, please feel free to ask me any questions.